Our basic material is the geometric series. The power series is a geometric series as a function of x. So that if I define a function of x, f of x equals the sum from n equals 0 to infinity, x to the n, and if I enroll that to see what I'm talking about, then because this is a geometric series with a equals 1 and r equals x, therefore, this will converge to 1 over 1 minus x as long as it meets the condition of the geometric series test, which is that the absolute value of x is less than 1. This is the fundamental material. Now, at this point, do you have any homework questions? I've got a spare here.
Oh, no, I just forgot my notebook.
Oh, gotcha.
Can I see the questions?
Our goal for today is to be able to identify forms and also to be able to do a little bit of algebra and calculus with these power series. Okay, well, let's talk about the identification of forms. First of all, let's consider what happens if we have a power series that looks something like this. First of all, unroll it so we can see what we're talking about. Being able to go back and forth between unrolled and rolled up or summation notation forms is one of the basic skills that you need to be able to have, because you're going to find that certain things are easier like this, and certain things that we do are going to be easier like this. So when I unroll it like this, it is very clear that I'm looking at a geometric series with a first term of 1 and a ratio now of 2x. Of course, that was clear from the original form as well. So that I can say that this will converge to a over 1 minus r if the absolute value of r is less than 1.
So a power series is kind of like a tiny geometric series.
A power series is definitely a geometric series. Yep. At least, yeah, at this point. And then what we're going to do is to generalize to Taylor series that are going to represent functions that will not necessarily be geometric series. Now I want to examine this inequality a little bit more closely, because this inequality is going to give us an important quantity, the interval of convergence. If I take this inequality and I explore it a little bit, what I'm saying is that this will converge for all x's such that 2x is between negative 1 and 1. Or in other words, that x is between negative 1/2 and positive 1/2. This value, this set is called the interval of convergence. And it is telling us all of the real numbers for which this series actually gives us a value and therefore converges to this closed form criteria. So this is the first thing that students have to kind of get used to, and that is that this equality is not absolutely true for every single real number. It is only true for the x values that are in the interval of convergence. Outside that interval of convergence, this closed form will give me a value, But this series will not. It will blow out to infinity. Or right at x equals negative 1/2, it will alternate back and the partial sums will alternate back and forth between negative 1 and positive 1 or something like that.
Oh, I have a question. Can you just put equal sign between this? They're not exactly the same thing, right? It's just different form, but they're not the same.
They are the same thing. They will give you the same values. If I take x equals, say, 1/3, and plug it into the series and add up, I will get a geometric series whose value is exactly 1 over 1 minus 2/3. So there is equality on the interval of convergence only. This is the big principle. On the interval of convergence only. Now, it's not too terribly surprising that we have a limited interval of convergence, because if you examine f of x equals 1 over 1 minus 2x, you can see that that function has a vertical asymptote right at x equals 1/2. So it is not too terribly surprising that my interval of convergence, which is from negative 1/2 to positive 1/2, not including, has to stop at the vertical asymptote. I'm not too terribly surprised that that happens. Okay. Now, if we characterize this interval of convergence in terms of numbers, then we get this interval right here, which I can also write like that. There's my interval of convergence. Easy enough. And I get the interval of convergence by considering the geometric series condition, that the absolute value of the ratio must be less than 1. Another way that I can characterize that interval of convergence is in terms of a center and a radius. In other words, as a neighborhood. And if I look at the center, that center is 0, and the radius of convergence is 1/2. In other words, I start at 0 and I go out 1/2 in either direction. This concept is more widely used when you get to multivariable calculus, because there your series will converge in a circle or in a ball with a center and a particular radius. For our purposes, a circle on a one-dimensional line is simply an open interval. Question? Okay. So this is the first thing, is to observe that within a power series, we end up with some sort of interval of convergence that can be characterized by a center and a radius. Let's see another example of this. When I look at this series, at first I think, oh, it's not in the power series form. And you're right, it's not exactly in the power series form. But if I unroll it, I observe that it can be placed in the power series form. If I write the first 3 terms, then I observe that I have a geometric series whose first term is 1 and whose ratio, common ratio, is x squared. So that, because this is a geometric series, I can apply the geometric series test and find that this guy converges to 1 over 1 minus x squared, so long as the absolute value of x squared is less than 1. And this will be true for all x's between negative and 1. In other words, on an interval of convergence that has a center at 0 and a radius of 1. And this format that you see right here is essentially the way that we take apart these power series. We identify the first term and the common ratio, unroll it if we need to make that happen, and then we apply the geometric series test to give the value of convergence, which is going to be a function of x, and the appropriate interval of convergence, just like that. You guys try one. Good. Find closed form interval
And then, where's N?
What's that?
And there's no.
Oh. The world. Thank you. Much better. If you are watching at home, go ahead and do this as well. We'll pause. Come back now. Okay, Danielle, what do you got?
I got.
Give me the whole logic.
So I open it up
Mm-hmm.
to 1 plus x over 3 plus x squared over n.
This is our standard form that we're going to unroll in, 3 terms plus an nth term. And let's use.
And a equals 1
Mhm.
and r equals x raised to 2.
Keep going.
So it equals to 1 over 1 minus x over 3.
Mm-hmm.
Simplify things.
Mm-hmm. Yep.
1 over x.
Wait, what?
It turned out to be oh no.
That's okay.
3 over 3 minus x.
Yeah.
If absolute value of x over 3 is less than 1.
Mm-hmm.
So x over 3 is less than 1, take it out.
Notice that Danielle didn't necessarily do this, but this is a great way to think about it. I can multiply both sides by 3 to get an inequality directly. You get the interval of convergence, -3 to 3. Yep. So the radius is actually not 1/3, but +3.
Uh-huh.
Yep.
Yeah.
And to find that, you have to appeal to this condition and solve the inequality. Okay, now one more little variation that we could have here is, what if we have the sum from n equals 2 to infinity
You
of
just say we can convert
x to the n? Yeah, we can convert it. And there's a couple of ways that we can think about this, but the easiest way is to unroll it. What is my first term going to be, Josh?
X squared.
Plus plus
X to the 4th.
and now when I write it like this, I can visualize it in geometric series format. First term is x squared. Common ratio is
X.
x. So that this converges to a over 1 minus r if the absolute value of x is less than 1. Ta-da. And so what I have done now is to find my closed form here, and I've got an interval of convergence there, and life is good. A second way that I can think about it is a little bit more subtle, and that is that I could consider this to be an example of index shifting. And if I consider this to be an example of index shifting, I could rewrite this by moving my index down by 2. So the starting index is going to go down by 2. But now to compensate in the form here, I need to increase all my references to n by 2. So that this and this represent the same series. Index shifting. We're going to use index shifting in some different forms later on. And now, when I unroll it, lo and behold, I get the same series. So that correctly shifted indices always give me the same unrolled form. But now, this isn't really in my geometric form, is it? So I'm going to pull off a little bit of algebra to rewrite my series here. Now here is the key. Students will get the n's and the x's vastly confused sometimes. The n is the index variable within the context of this sum. X is a constant with respect to n. This sum is a sum for a given value of x, which means that that constant can be pulled to the outside of my sum simply by factoring it out. I'm literally factoring out x squared from all my terms. And now I have the standard geometric series with the interval of convergence of -1 to 1, and the value of 1 over 1 minus x. In this particular case, this right here was harder to do than doing it with the unrolled form, but that's not always the case. Index shifting is sometimes easier than working with the unrolled form, and vice versa. That's why we need to be able to do both skills. What I'd like to do now is to consider the algebra of power series, and we're going to follow that up with the calculus of power series. But are there any questions about either method here? Either unrolling the series and identifying A and R, or index shifting and doing a little bit of algebra here.
I've noticed
power series are geometric series. And a geometric series is in the form the sum n equals 1, infinity of AR to the n minus 1. Or I could write it as the sum from n equals 0 to infinity of AR to the n by index shifting. And so we're referring to the A and the R from the geometric series, and we are appealing to the geometric series test when we do this conversion. A over 1 minus R. Okay. Now, let's consider the algebra of power series. First of all, constant multiple rule. If I have any function of x multiplied by x to the n, which is a constant in terms of my index, then I can pull that constant to the outside. Second, let's see. Maybe I can do it like that. That. And then what I get is exactly the same as this right here. In other words, I can split a power series term by term. Not all sums can be so done. We'll take a look at issues of convergence later on, but power series are in the category of series whose sums can be split and added term by term. Now let me show you just one example that's kind of cool. Actually, let me write it like this, so that it's a little more clear. There we go. Like that. Okay. So I have power. I have really what looks like two different power series being added, right? So first, I appeal to the sum rule and split them. First term, it's pretty clear that the first term is equal to 1, so n equals 0, and the common ratio is x. And the second term, it's pretty clear that the first term is 1,
Negative x.
and the common ratio is negative x. So that now I can rewrite both of these as 1 over 1 minus r, for absolute value of x less than 1, and 1 over 1 minus r for the absolute value of x less than 1. Again, it's technically the absolute value of the opposite x. These have the same interval of convergence. If they did not have the same interval of convergence, we would have to take the intersection of those two intervals. These have the same interval of convergence, and therefore I can say that this whole thing collapses to this guy right here. That's a perfectly good fraction, but if I combine to get a single fraction, then what I get is 1 plus x plus 1 minus x over 1 minus x times 1 plus x, or in other words, 2 over 1 minus x squared. Now this is very interesting, because previously we got a series whose value was 1, nope, not here. We got a down, where did it go? Here. No. There. We got a series whose value is 1 over 1 minus x squared. And now I have a new expression whose value is 2 over 1 minus x squared. Shouldn't those be related to each other in some way? Ah, but they are. If I take and unroll the first few terms of this series, what I get is 1 to the 0 plus negative 1 to the 0. I'm sorry, x to the 0 plus negative x to the 0 plus x to the first plus negative x to the first plus x to the second plus negative x to the second and clobbers. The negative sign clobbers. Plus x to the third plus negative x to the third plus x to the fourth plus negative x to the fourth. Etc. Everybody see how I'm unrolling these terms here? Now we notice that all of the ones with odd powers cancel out. And what I get is 2 plus 2x squared plus 2x to the fourth, etc. And only the terms that have even powers are left. And if I go back and compare that to my original series right here, it's the exact same series multiplied by 2. So the moral of the story is that unrolling series can give us additional insight as to what's going on. So that's our algebra. We can add, subtract series. What about multiplying series? Ugh, it's gross, don't try. Think about it. At some point, far in your future, you will learn how to multiply series effectively. We're not going to worry about it in this class. But let me give you just an idea of what this would look like. This would be equal to A0 plus A1 plus A2 B0 plus B1 plus B2. And we have an infinite number of distributed properties that we have to worry about. We get A0 B0 plus A0 A1 plus B1 plus A1 B0 plus etc. And it just gets really, really gross really fast. So, good news, we don't have to worry about multiplying series. We only have to worry about adding and subtracting.
Will there be a 0 here?
No, no. Yeah, it's kind of awful. Oh, it totally can be done. It's just that it gets yucky. And unless you happen to notice some patterns and create some recursion relations, don't mess with it. Yes, sir.
So I didn't get it done my high school years.
Nope. Yep. You're welcome. Okay. Now, what about the calculus of power series? Fortunately, because of the algebra of power series, the calculus of power series.
So is it gonna be a derivative of the closed form then?
Yes, that's it.
Oh.
But the only thing that we have to worry about is our index a little bit. Okay? So if I take the derivative of x to the n, using the sum rule for derivatives effectively, I can march down and write that as the sum from n equals 0 to infinity. But wait a second. That first term disappears. That first term disappears because it was a constant in the original and gets clobbered, or because 0 times x to the minus 1 power is 0. However you want to think about it. But also, if we take a look at our result here, This is the derivative of 1 over 1 minus x. And we get negative 1 over 1 minus x quantity squared times the derivative of the inside. And what we get now is a power series representation.
What is the sum of n equals 0 to infinity and then the n minus 1 equals the last one? Is that it?
Unroll the first few terms. What do I get from the first term?
First term is 0.
For that one, for the second one, the first term is 0.
Uh-huh.
For the third one, the first term is 1.
So let's write out the first few terms. We get 0 plus 1 plus 2x.
Okay.
Right? So they're the same. Right. And so we get this is equal to this closed form. Now, what about the interval of convergence? Good news. When you take the derivative of a power series whose interval of convergence is an open interval, you get the same interval of convergence. Later on, when we do Taylor series, the interval of convergence may contain an endpoint, and that endpoint is not guaranteed to convey. Very similar to what we did with piecewise functions at the joint. So the interval of convergence is still going to be for x's that are between -1 and 1. Now, the same thing, now I want you to notice I cheated a little bit, and I didn't really tell you that I was cheating, and it was okay that I cheated for the power series, but I want you to be aware of what's happening. What I did here was to switch the order of operations. I brought the derivative inside the sum. You see it?
Oh, I thought you just forgot to write.
No. What I did was to bring...
You did the inside.
Yes. Is that legitimate? And the answer is not for every series, but for
This one.
power series. The same kind of consideration is true here.
Nice.
And that is that if I integrate the geometric power series here, then what I get is a term at a time integration of each term. Plus the mandatory constancy. So in other words, power series behave themselves very well. I can take derivatives, I can take integrals, don't forget your C, and there it is. So for example, when I integrate the series x to the n, then what I get is the series 1 over x to the 1 over n plus 1 x to the n plus 1 plus the mandatory constant c. And I can write out the first few terms here as, I'll put the c first, c plus x plus 1/2 x squared plus 1/3 x cubed plus all the way out. And what does that converge to? Well, it converges to the integral of the closed form, which is negative natural log of 1 minus x plus c. So this is fascinating because what I have done now for the first time is to create a series representation for a function that is nowhere near a polynomial. Isn't that interesting? We actually have a way to compute the logs of numbers by representing them as series. By the way, what would this value of c be for the function ln of 1 minus x? Wow, representation. What is a series representation of ln of 1 minus x? Well, let's take our work here and modify it just a little bit. We know that the negative of ln of 1 minus x plus c is equal to all of this. So let's first of all take the opposite and say that ln of 1 minus x is going to be some constant c minus x minus a half of x squared minus a third of x cubed dot. And now let's find the value of c by plugging in a known value. Specifically, I'm going to plug in x equals 0, the center of the interval of convergence. If x equals 0, then I get ln of 1 minus 0 is equal to c plus nothing. And therefore c is equal to 0. And I come to the conclusion that ln of 1 minus x is negative x minus a half x squared minus a third x cubed plus nothing. This is impressive and powerful because it gives us a possible approximation tool. So, for example, suppose I wanted to use this series to estimate the natural log of 0.4. Then I can do that by, first of all, finding the value of x that corresponds, which is 0.6. And then I can say that the natural log of 0.4 is approximately equal to, and now I can pick as many terms as I like to get as good an approximation as I like. So let's say I take two terms, approximately equals minus 0.6 minus a half of 0.6 squared, or 0.36. Half of 0.36 is 0.8. I get minus 0.78. How does that compare to the actual retail value?
It's not that close.
It isn't that close, you're right. Should have been a little better. I wonder if we did something wrong here. Did I do something wrong in the integration? Did I do something wrong in the evaluation? X is 0.6. I just have to, I guess, so the actual is, what was it, negative 0.9?
9162.
Okay. So that's not very impressive, and I guess it's not very impressive because our series is slow to converge.
Yeah.
We're going to see that issue later on with the speed of convergence. So this is not a great approximation for an x as large as 0.4.
Yeah. So without calculator, you would know like how precise is the rule.
Right, that's right. So we can
Yeah.
compute an error and get a truncation error. We'll actually cover that tomorrow. Let's do one more example and then we'll call it a day. So let's consider this problem right here. Express 1 over 1 plus x squared as a series, give its interval of convergence.
We've done this.
Almost. We did 1 over 1 minus x squared.
Oh, minus.
Yeah. So if I am going to express this as a series, then I'm going to think about it as, yeah, we're going there. We're not there yet. We're going to have to think about it as a geometric series. And we're going to have to identify the A and the R that we're talking about. So the magic form that we're looking for is to find the A and the R that make this happen. And it seems pretty clear that the easiest way to do this is to let A equal 1 and to let R be negative x squared. And now that I have that expressed in that form, I can go back and write a geometric series that corresponds to A. Well, let's just do it in the summation. It's going to be the sum from n equals 0 to infinity of A times R to the n. This is perfectly fine, but very often we want it simplified, and so we can simplify that as the sum n equals 0 to infinity of negative 1 to the n times x to the g. And if I were to write it in unrolled form, it would be 1 minus x squared plus x cubed. Does this make sense to everybody? Yes. Justin, you good? Sure. Okay. So we can go one further. Express arctan of x in series form. Now, I look at this and I go, there is no way I can put that in geometric series form. So let me play around with some calculus and see if I can get anything. Let's find the derivative of arctan x. Yep. Since the derivative of arctan x is 1 over 1 plus x squared, I can therefore say that arctan x is the integral of 1 over 1 plus x squared, which is now the integral of my series like so, pulling in the series that I had for 1 over 1 plus x squared. The big theme here is that I can replace the function in closed form with its series on the integral of convergence. So now I can go through and integrate term at a time, and I get the sum from n equals 0 to infinity. Negative 1 to the n is a constant. 1 over 2n plus 1, x to the 2n plus 1. And usually we tuck our c out front, equals c plus. To find that value of c, we're going to use the known value at the center of convergence. Arctan of 0 is c plus nothing. Notice that for all n, my terms will all be 0 at the center. So that I get 0 equals c, and I have my series representation. Arctan x equals sum n equals 0 to infinity. Negative 1 to the n, x to the 2n plus 1 over 2n plus 1. If I want to see what this is looking like, I can unroll it. My first term is going to be x over 1. My next term is going to be minus x cubed over 3. Just like that. So this is our very first foray into representing series as, representing functions as infinite series.